So here's a super neat example, which is the next one that I want to be able to go over. So there's a few examples here on related back to kind of energy, work, power. So the first one is calculate the mechanical energy, kinetic energy, and gravitational potential energy at each of the points, okay, on this roller coaster that you see here. Now assume the mass of the cart at the and the person is 385 kilograms. Now notice it has an initial speed there as well, right? So that it's kind of starting off at. Now neglect friction, okay, and then air resistance in the problem. So in those instances, whenever we neglect kind of frictions, air resistances, then what we are going to be dealing with is that the mechanical energy that you have at any point, if it's at A, if it's at B, okay, if it's at C, it is always going to be the same. Now, it's not realistic, but for introductory physics, that's something that we often will do, where we neglect frictions and resistances just so that we understand the concept of the transfer of energy. All right, so let's take a look and try to see if we can knock off all of these, and we'll do it kind of point by point here. All right, so the first one, okay, we're going to start with, so this is at point number A. So we know that the mechanical energy is equal to the kinetic energy plus the gravitational potential energy at that particular point, right? So let's take a look at kinetic energy. So this is the kinetic energy, which is 1/2 mass times the speed squared. Now it turns out that we know both of these. So we know the mass, they give us the mass, which is 385 kilograms, and we know the speed, which is 14. So that's not going to be very difficult for us to do. So I can take 1/2, 385, it is all in metric standard units, so this is much simpler. All right, so let's take out our calculator. So this is going to be 1/2 times 385 times 14 squared. So that's going to be 37. I'm not going to round anything, okay, in here. I'll just keep it the way that it is. So this is joules. Now the gravitational potential energy, on the other hand, so that would have been gravitational potential energy here, is going to be mass times the gravity times the distance or the height, okay, so whichever way that you write it, with regards to the distance away from some reference. So now in this case, they're referencing the point 35 meters kind of from the bottom, okay, all the way down, possibly the actual ground. So in that case, again, so what we will have, the mass itself, so that's 385. The gravity, we'll assume it's 9.8 meters per second squared. That's the acceleration. And this is 35 in terms of the height. So now let's push that into our calculator. That's going to be 9.8 times 35 equals, so that's 1,32055 joules. Now that we have both of these taken care of, so that's 1 kinetic, that's 2 gravitational potential energy, so I have both of these, so notice these two are present there, so I can certainly calculate what the mechanical energy is. Well, so the mechanical energy in here is going to be the summation of the two. So that's going to be this plus this. Okay, so I have this already on the calculator. Plus, so it's going to be 37730 equals, and that's 1,69785 joules in total. That would have been the mechanical energy that you have. Now, again, I'm not going to round anything. If you need it to round, you can round to whatever significant figures you have been asked to for this question. I'll just leave it as it is for the moment. So that would be A. Now, once we have A, this problem actually becomes much simpler, because then we can calculate what the mechanical energy is everywhere, and it's always going to be exactly the same. So mechanical energy, and this is for the point B, is going to be identical. I don't actually have to calculate anything, because if I assume that there is no more friction, okay, at all, and no resistances, then I know that mechanical energy just transfers, and it's exactly the same all the way throughout. So I know that. And now, what does this do? So at this particular point B, well, it helps me a lot, because if I go back and I start thinking, okay, so what's my kinetic energy, okay, in here, and then what's my my gravitational potential energy in here, so I can obtain these two rather easily. Now, so you can calculate the gravitational potential energy very, very easily, right? So I don't actually know the speed at 18 meters. I can find it, I can use kinematics to do it, but please don't, right? Just make your life simpler. So meaning that now you can just say, okay, well, my gravitational potential energy are these three. However, the only thing that changes is the height, right? So if in here, so let me just remove that out. So I have 385, the mass is the same. Obviously, gravity is not going to be changing. Now, the height in here, it's now 18. So that gives me 67,914 joules of gravitational potential energy. So if you want kinetic energy, then that's going to be just mechanical energy minus the gravitational potential energy. That's because of the law of conservation. So the energy just simply transfers back and forth. So that means everything else must be kinetic. So if you take this, so 169,785 minus the 67,914, so now all of a sudden it's going to be 101,871 joules. And that's your kinetic energy at point B. All right. And now you can repeat the same thing. So, I can take this whole thing and then start doing exactly the same thing. So with regards to point C. So now that point C is now 25 meters away. So again, so what do I know? I know that mechanical energy is going to be constant. Okay, so this doesn't change. So this is a really nice trick in here. And again, so I can go back to kinetic energy and then gravitational potential energy. Once again, I know that the height, okay, that I have in here, so within here, so that's 25. So I can find my gravitational potential energy, mass times gravity times the height equals, so 385 times 9.8 times 25. So you're going to have a little bit more of gravitational potential energy as it goes back up right there. And then your kinetic energy, again, is going to be your mechanical energy minus your kinetic energy, okay, as a whole. So with that, so if I go back in here, so it's 169,785 minus 94,325 equals, and that is going to be 75,460 joules. And there you have it, right? So now you've calculated all of the points A, B, and C on this roller coaster. This is a really good exercise for you to be able to understand, and in particular, think about the law of conservation and how energy transfers between kinetic energy and gravitational potential energy if you assume that you are neglecting friction and air resistance. Now, if you do not have this case, then there's all other kinds of energies that are going to get involved in the transfer. But if you neglect it, this is exactly what we would do. All right, so now tied in, so here's the another example which is related back to kind of what we had just above. And it says, what is the gravitational potential energy in the previous question at point C relative to point B? So this is a good question to ask yourself, because one thing that oftentimes we forget, okay, as learners, is that gravitational potential energy, right, which is this, is mass times gravity times this height, or times the distance, okay, however you want to write it. Now, this height is always relative to something, And now the question, of course, is relative to what? Most of us think that it's to the actual surface of the ground, but it doesn't have to be, right? It can be gravitational potential energy relative from one point to another, right? So from this point, to the surface of this table, right? What's the gravitational potential energy between here? And that would be my height. Now to the floor, okay, it's going to be a bigger height. So I have more gravitational potential energy relative to that floor. So if you go back in here and you kind of take a look Now, I don't know if this is going to let me do it or not. Again, I'm going to just try. Okay, so here it is. So we have these two particular points. And so what is happening here is, okay, so we have with respect to this, okay, and then with respect to that. So my height, okay, right here, so point C relative to point B, this would have been my height. Now, of course, that height is equal to 25 meters minus the 18 meters, or really just, 7 meters in total. So your gravitational potential energy in here would have been, the mass doesn't change, the gravity doesn't change, but the height is now only 7 meters with respect to that. And that's worth knowing, right? So that your gravitational potential energy is always with respect to a reference. And if we wanted to calculate what that is, 9.8, times 7 equals, and that would have been 26,411 joules. Again, you can round to whatever you want, okay, in here. So here's just 3 sig figs if that's what was asked, okay. But of course, just check with your teachers as you are doing that. And that would be it, okay, for this particular example. The next example here, it says a physiotherapist is working with a patient who has a mass of 89 kilograms. The therapist has asked the patient to climb a flight of stairs. The flight of steps, okay, has 25 steps with each step being 8.5 inches in height. What is the power output of the patient, okay, if she completes the exercise in a minute? All right, so hinting us, towards gravitational potential energy. So basically what you have is, you have a bunch of steps, okay, and, you have someone who's climbing these particular steps as you're going through, and of course this just continues on. Now, we have 25 of these steps in total, so 25 steps in total. Now, as you can see there, each step is a particular height. So it tells us that each step has a height of 8.5 inches. Now, let me just convert it back in. They give us the conversion right there. So 8.5 inches, I'm going to just convert this back to meters. So 1 inch. Notice it says 2.54 centimeters. Which is really 0.0254 meters. That's because of the prefix. So we have that. So 8.5 multiplied by 0.0254. So that's for just one step. So 0.2159 meters. This is per step. Now we have 25 of these steps. So I'm going to multiply this by 25. So for 25 steps, right, the actual height is going to be, 5 meters, 39.75. Again, I'm going to just keep the decimal places for myself here. So that's what we would have. Now, that's just the height, right? Now, in terms of the power output that we have in here, so really, this is more so for the power input, meaning the, how much energy, okay, are you going to be going through to try to get you to the top of the stairs. Now, the reality is you're going to actually have a bigger output than that, because as you're climbing stairs, it's not just the process of climbing a stair. You're not just getting your body, okay, up on top there. There's all kinds of other things happening internally within you, right, to be able to climb those stairs. So this calculation, because from the hint it says, equated to your gravitational potential energy, we're just really looking, okay, at the gravitational potential energy that we would have to overcome to climb those steps. And we're not calculating anything, internally that is happening within our body. All right, so with that in mind, that means that the energy, okay, that we're going to have to overcome is going to be, so the work done is going to be mass times gravity times the height. Now this patient is 89 kilograms. 9.8 meters per second squared is acceleration due to gravity. And then I have this total height for the steps. So this is what our energy would be. So I have this already on the calculator, so times 9.8 and then times 89. All right, so it's not going to be that much. Okay, so if you think about it, and this is, pretty much just a calorie in here. Okay, so this one maybe I should round, but I'll just leave it just for the sake so you can compare your answers there, okay, if you're doing this question with me. So that's what it would be unrounded, and then obviously, about 4,700 rounded, which is just a little bit over 1 full calorie in here. All right, so now they don't ask us for the amount of work, right? So this is the amount of work that we would have to do, okay, to bring us up to that gravitational potential energy. They actually ask us for the power. Well, so if this was happening in a minute, so remember, power is equal to the energy or the work divided by the change in time. And that's going to be, 4707 ... etc. divided by a minute. Now be careful here because a minute is 60 seconds, right? So we have to kind of put those back into metric standard units. So my answer divided by 60, and that would have been 78, I'll round this to 3 sig figs, 78.5 watts, okay, or joules per second. That is going to be your power output, okay, that you are going to go through for this example. And that is it, okay? So that's all that you would have here. Here's the last example. So a medical device is transferred, so 4.2 kilojoules, okay, of desirable energy in 25 milliseconds, all right, okay, into an X-ray image. So if the device utilizes energy at an efficiency of only 1.5%, so not very efficient, then what is the power needed to complete this process? Okay, so there's a few things happening in here. So in terms of energy efficiency, so don't forget that the energy efficiency is equal to whatever your energy output, okay, is. That's the useful energy divided by the energy input, okay, that is the total energy that you actually input. And this is always times 100%. So what do we have here? Let's write down the givens. So a medical device is transferred 4.2 kilojoules of desirable energy. So desirable energy is basically, okay, the useful energy that's outputted. So I'm going to put this, okay, in here. So energy out is, and I'm going to put this in metric standard units, okay, so joules. So I'll just convert from kilo. The time, the total time, and again, please be careful here. So I'm going to change it back to seconds because they give it to us in milliseconds. So that's what I have there. Now we can't just take this and then divide it by that. So with regards to this, so it says that what is the power needed to complete this process? So the power needed that we would have, that would have been the power in, which would have been your energy in, okay, over the total time that it took. Now, we have, at least up to this point, okay, we have this. We have energy out. We do have the efficiency. So notice that this efficiency is 1.5%. So I can solve for energy in. And now once I have it, I can substitute it in here and divide it by the time. So let's do that. So 1.5%. So now that's going to turn back in because divided by that 100. So that's 0.015 is equal to the energy out, which is 4,200 joules divided by energy in. So I can solve this. So energy in is equal to 4200 divided by 0.015. All right. So let's take a look at that. It's going to be probably a big number there. So 4200 divided by 0.015. Yep, so it's pretty big. So we need quite a lot of energy, okay, if it's only 1.5% efficiency. Now that we have this, we can calculate our power. So our power into this whole system is going to be your, okay, energy that you have. That's in joules. And our time is now also and this is 25. Okay, seconds. So this is joules, this is seconds. So we're going to get watts out of this. So let's take that and divide it by 0.025. All right. So power in is 11200, okay, this is watts, or as you can see there, that's 11.2 megawatts, right? So that's quite a bit of power. And the reason for it is because this energy, okay, so this amount of energy, and this is, pretty substantial amount of energy that we have in here, but it's not enormous. The only thing is that it's being transferred in 25 milliseconds, so it's really fast. So that means you need a lot of power, okay, in order for this process to kick in. Now, this is already actually to 3 sig figs, so if that's what you have to round to, there you have it. All right, so that's the last one. This is an amazing example, just to make you think about efficiency, okay, and then relating it back to power. Okay, thanks for watching. See you in future videos. Bye, everybody.